Okay, now just going back to where we left off in the case of functions. And again, by definition, okay, this is from last time, a function is a mathematical relation where in the xy coordinate system, for each x value, there is one and only one corresponding y value. And again, all ordered pairs are of the form xy. And again, x is the independent variable or the input variable, and y is the dependent or output variable. And again, we had just in the case of examples of sets that are functions as well as those that are not functions. Again, if you have again only one y value for each corresponding x value, okay, it is a function. And again, what's referred to as the domain will be the set of x values, and what is regarded as the range will make reference to the set of all y values. And again, just in the case of ordered pairs, okay, if you have if you have a repeating x value and the pairings are different, that is, if you have different y values, then the relation fails to end up being strictly defined as a function. Okay, and again, we have our samples of functions as well as situations, okay, where we fail to have functions. Again, if you have the same x value and we have in the set, you have repeating the x value and the repetition of the x we have with the different y value. Okay, so again, we have to fail to be a function. And then just sort of expanding the horizons in the case of what will constitute a function. And again, an ordered pair is kind of like a granular way of looking at whether the relation is a function. And we have, let's say if you have in the context of graphing, okay, now in graphing, okay, there's one particular test that the function is going to satisfy. And this will be what is referred to as the vertical line test. And this is just a visual way of saying that for each x value, there is only one corresponding y value. Okay, and so we have, in the case of the vertical line test, and for the vertical line test, okay, you will have like a vertical line will not intersect the graph of a function Okay, so a vertical line will not intersect the graph of a function at more than one point for each x value. Okay, and just taking what we have, say using the vertical line test. And say if we have whether the graph is going to be a function or not. Okay, and okay, and say we have with, again, utilizing the xy coordinate system. and just doing a bit of a sketch, and I'm going to bypass the number labeling. Okay, but again, you have the x-axis is a horizontal number line, y-axis is the vertical number line. Okay, and let's say if we have, for instance, okay, we have a graph. Again, I'm just going to sketch. There we go. And we'll say that we have, we'll say we have the graph of y is equal to 2x plus 4. Alright, so I'll just go ahead and lay out the functional notation. I'll explain this in just a moment. So you have y is equal to f of x is equal to 2x plus 4. And let's say if we take a vertical line. And you have to run continuously from end to end. Notice you have in the interaction, you're going to have this vertical line from end to end is going to intersect at most 1 point for each x value. Okay, and so this is going to be a case of a function. And y equals 2x plus 4. This is going to be a case of a function that runs continuously. And let's say that if we have, let's kind of take something, like a clearly explicit function, at least not in terms of something like y is equal to 2x plus 4. I can have something that's just sort of split up, or a graph that is split up. Okay, so if I run a vertical line, let's say from end to end, okay, so you have no intersection, then once you get to this zone, for each x value there is at most 1 point of intersection. Okay, then we have no point of intersection, then you have, for this segment, you have at most 1 point of intersection, then you have no point of intersection, and then for the rest of this particular section, okay, we have have at most 1 point of intersection. Okay, so this is also a function. And let's say if we have let's see. Okay, now let's say we have a circle. And let's say we have this to be defined. Okay, now this is going to be a circle whose center is going to be the origin. That is where the x and the y axes will meet. And we'll say we have defined by the equation we have, x squared plus y squared. is equal to 4. Okay, and you have like, if you were to throw in any points, okay, you have like 0, 2, 2, 0, 0, -2, and also -2, 0. Okay, I'm just kind of giving you a little bit of Math 172. Okay, but just kind of bringing it back down in terms of what we have in Math 171 terms, okay, whether we have a function or not. Okay, now what's going to happen here, okay, is that, say if I start from left to right, and we have at -2, 0, and then I proceed the least bit to the right, well, guess what? To be a function, it must satisfy the vertical line test, and it says a vertical line will not intersect the graph of a function at more than 1 point for each x value. And guess what? The vertical line test is going to be violated. So here we have 2 points of intersection. At the same x value. And because of this, okay, something like x squared plus y squared is equal to 4. Okay, this is not going to be a function. And if I were to make an adjustment, okay, and I think I'm known to be posed this particular question. Okay, so whole circle, because you got the bottom and the top halves. Okay, and I've been asked, okay, could a semicircle be a function? Well, if it's the right kind of semicircle. Okay, so just kind of taking what we have and sketching. Okay. And let's see. See, if I took the upper half, okay, so just like the upper half of what was this circle. And you have intersection at most 1 point. So semicircle of this type, okay, now this is going to be a function. And in fact, for this semicircle, this would be in reference to, if there were an equation for this, you would have that y is equal to f of x is equal to the square root of 4 minus x squared. Okay. And this one is going to be a function. And just kind of give you a kind of a composite summary, especially with semicircles. And whether we're going to have a function or not. So you have, for instance, okay, say if you have upper half, just like what we had a moment ago. So just kind of doing kind of a quick sketch. this would be a case, once again, of a function. Okay, and say if I have like a left half. Like the left half of a circle. Well, guess what? Just, if you notice, you have it the same x value, you're going to have violation. So this would not be a function. And say if I have bottom half, about like a bowl. Okay, so if I have going, say, moving a vertical line, okay, from left to right, you're going to have intersection at most 1 point. So this would be a case of a function. You have, in the case of the right half, say of a circle, and I ran a vertical line through this. Okay, you would have at some sets of the same x values. Okay, you would have the intersection at 2 points between the semicircle in the form of the right half of the circle and a vertical line. So again, this would be a case of something that does not quite turn out to be a function. And just the for this particular setup we had moments ago. And say if I were to take away or add, I'll do this. I have almost the same thing once again. Okay, say if I ran a vertical line, okay, but upon adding this particular segment, guess what? There's a location where you had the same x value and 2 points of intersection. Okay, so in order for the graph to be a function, it must be that for all x values. Again, running from negative to positive infinity, there should be at most 1 point of intersection between the vertical line and anything that pertains to the graph of the function. In this particular case, we have at, say, like for this location of x, you have at least 2 points of intersection, okay, between the graph of what could have been a function and the vertical line that tests this. Okay, so again, so not a function. Now, looking at what we have concerning functional notation. Okay, so for what we have in the case of functional notation, okay, now, and still working within the xy coordinate system. Okay, now if you see anything like f of x or g of x, this f of x will be in reference to what we otherwise refer to as y. And in this particular sampling, okay, so f of x is a functional notation for y. And again, we have with the letter x, X is going to be the input or independent variable. In the case of what we have for Y, again, Y is the output or dependent variable. And just crossing over to, let's say, in the realm of functional values, equations, all that. Okay, in the realm of determining functional values and expressions. And just taking as a sample, okay, see if we have given, okay, y is equal to f of x is equal to x squared minus 3x. And you're to determine just what the y value is, let's say, or y expression is going to be, let's say if you have determining y whenever x is negative 3, and also determining y whenever x is at 1, and also what the variable expression will be whenever we have changing over the input from x to the binomial x plus 2. Okay. So we have in our expression, okay, for the given function, we have once again, okay, we have f of x is equal to x squared minus 3x. Now for f of negative 3, okay, so I'm switching over, okay, from x as the input to negative 3 as the input. And in the determination of the output, okay, so wherever we see x, we'll replace that with what is inside the parentheses. So x squared becomes the square of negative 3. And we have minus 3x, which will become minus 3 times negative 3. And here we have the square of negative 3 becomes 9. Negative 3 times negative 3 becomes another positive 9. And 9 plus 9 is equal to 18. So, way of looking at this, okay, is that, okay, so you had the input x, which was at negative 3, and the output y, okay, that's your function value whenever x is set to negative 3, so we have 18. So just as an ordered pair, you would have negative 3, 18 as a point that would be on the graph of y equals f of x is equal to x squared minus 3x. And for what we have with the input at 1, okay, so you have it x squared, so this will become 1 squared. Negative 3x becomes negative 3 times 1. So you have 1 squared is 1, and you have minus 3. And 1 minus 3 is negative 2. Okay, so we're looking at specified point here. So we have x equal to 1. We have y is equal to negative 2. So a point on the graph of this function we have along with negative 3, 18. We're also going to have 1, negative 2. Now, extending from x out to x plus 2. Okay, so transitioning, looking at not a specific point, but just looking at a change in the dynamic of the general output as we go from x to x plus 2 for the input. Okay, so we have for f of x, we have the square of x minus 3 times x. But now, again, f of the input equals the square of the input minus 3 times the input. And this is the pattern we have followed through whenever we had negative 3 and 1 for the inputs. But now, with the variable expression x plus 2 as the input, now the square of the input, we're going to have the square of x plus 2. And we have minus 3 times all of x plus 2. And again, just a reminder, the square of x plus 2 we have x plus 2 times itself. Many will make the mistake of just assuming it's going to be x squared plus 4. Well, they will be 2/3 of the way right, but again, you have your outside and inside products to add up. So you have not just x squared plus 4, but x squared plus 4x plus 4. And just carrying over what we have here. So we've got x squared plus 4x plus 4, and then with the distribution of negative 3 over the quantity of x plus 2, so we have minus 3x minus 6 and so for what we will have here, okay, we have the output to end up as x squared. We have 4x minus 3x, okay, it leaves us with x, and 4 minus 6 becomes negative 2. So we have, in this end result, we have x squared plus x minus 2. All right. Now let's say that just working with functions and determining functional values and expressions. Now we'll say we have given f of x is equal to 2x squared minus 3x plus 7 let's see what we get for, let's say we have f of negative 3 f of 5 and also f of x plus 1. Okay, so for this function, let's see what specific outputs we have whenever the inputs are negative 3 and 5. And also, let's see what expression we get whenever the input is adjusted from x to x plus 1. Okay, so looking at the functional values and expressions. Okay, so this time we have f of x set equal to 2x squared minus 3x plus 7. And if I have the input at negative 3, so having x to be represented by negative 3, we want to have f of negative 3 is equal to 2 times, okay, the square of negative 3. Then we have minus 3 times negative 3, followed by the addition of 7. And so we still have 2. Now the square of negative 3 becomes 9. Negative 3 times negative 3 becomes a positive 9. And again, we have plus 7. And we have 2 times 9 is 18. And you can go ahead and add the 9 and the 7 together, but we'll just do it step by step, going from left to right. So you have 18 plus 9 is 27. 27 plus 7 is 34. So whenever x is at negative 3, okay, the corresponding y value, f of negative 3, turns out to be positive 34. Okay, now for the input value at 5, okay, so we have in the follow through on this one, okay, so we have x to be represented by 5. So we have 2 times, okay, the square of 5 minus 3 times 5. Again, we have followed by the addition of 7. Okay, and here we have 5 squared is 25. And we have negative 3 times 5 is negative 15. Okay, we have the addition of 7 to trail. And here we have 2 times 25 is 50. And we have minus 15, which is going to be 35. And we have plus 7. Okay, so we'll have the output at 42. Now for the variable expression input with the binomial x plus 1. So this is going to translate out to 2 times the square of x plus 1. We have minus 3 times, okay, the quantity of x plus 1. And again, we have followed by, okay, the addition of 7. Okay, and again, just with the square of x plus 1, you have x plus 1 times itself. So this would end up being x squared, and the outside and the inside products would add up to 2x. Again, 1 times 1 is 1. Okay, then for negative 3 over the quantity of x plus 1, okay, so this would be minus 3x minus 3. Yeah, followed by the addition of 7. And distributing. Okay, so 2x squared plus 4x plus 2 minus 3x. And go ahead and say negative 3 plus 7, which will be positive 4. And just combining the terms. Okay, so you have 2x squared. And for what we have in x, 4x minus 3x leaves us with positive x. And we have, with the constants, 2 and 4. Okay, so this will come out to positive 6. Okay, so variable input in this case with x plus 1 leads to a variable output, in this case with 2x squared plus x plus 6. All right. And now, I had mentioned the other day when we were looking into the ordered pairs that the term domain, okay, would keep surfacing and resurfacing. And in the case of what we have as the domain of a function, and I had mentioned the other day that for sets of ordered pairs, the domain would be the set of x values. And just taking what we have here. Now, essentially starting with chapter 1 and going throughout for the rest of the course, we're going to kind of leave the complex number system behind and just stick exclusively with the real number system. And in the case of the domain of a function, Again, we have for the function, okay, we have y is equal to f of x. Okay, so for the domain of a function, y is equal to f of x, okay, this is going to be the set of all x values. You see we have the set of all x values or inputs. Such that the function y equals f of x is going to be defined in the real number system. Okay, so basically the purpose of the domain is just keeping the function real. Okay, so in another way, you probably heard the phrase keeping it real. Well, in the mathematical sense, this is what we have with domain. Okay, and let's say if you have if we're looking at determining the domain of the following. And you're to express the results in interval notation. And we'll say we have, first of all, if we have a function, and we'll say that we have f of x is equal to 3x plus 7. Okay, and in this one, okay, so we have for the domain of this function, okay, you're going to have a linear function, okay, and we don't have anything like an even root radical or anything like a fraction. So in this particular case, right, a function that like this is going to have no restrictions. In other words, there's nothing that keeps x from being any positive number or negative value or even from becoming 0. And because the function has no restriction, it's going to turn out that for the domain, you're going to have the set of all real numbers. Again, that's going to be denoted by parentheses around negative and positive infinity. And if we have, let's say, a function, and let's say we have something like 2x squared minus x plus 7. Okay, now all the variable terms are given in direct fashion, and so a little bit of history to repeat. We don't have a fraction or an even root radical, so again we have no restriction. Once again, the domain is going to be the set of all real numbers. And let's say that if we have, just sort of changing things up a bit, if I have, let's say, f of x is equal to 3x plus 4 all over x minus 5. Okay, now in this one we do have a fraction. And again, for a fraction to be defined, the bottom part of the fraction cannot be 0 in value. So guess what? Okay, we have from this, we have the x minus 5 cannot be equal to 0. And so in terms of what x cannot be equal to, it turns out we have the restricted value of 5. And for what we have as a consequence, okay, the domain, okay, is no longer going to be the set of all real numbers. It'll be those values of x with the exception of 5. So in terms of splitting up, you're going to have at the one end you'll have like going from negative infinity up to say 4.999, but not including 5. So you have 5 in the parentheses, and then you have like going from past 5, like 5.00000, and still greater than 5 itself. So you have for the upper half, okay, you have those values that will be greater than 5. Okay, so x is not equal to 5. So this notation here, you have all values of x less than 5, and the notation here denotes all values greater than 5. So this signals that we have only the number 5 excluded. And let's say that if we have a ratio, and say we have f of x is equal to, let's say we have x squared plus 7 all over x squared minus 16. Okay, and I'm going to provide a little bit of a visual here. So we have between the sets of terms here, okay, we have in the denominator, okay, we have x squared minus 16. Again, this cannot be equal to 0. And with the difference of squares, if the entire difference of squares cannot be 0, then neither can its factors. So neither x plus 4 nor x minus 4 can be equal to 0. So if x plus 4 cannot equal 0, okay, so you have the x cannot be negative 4. And if x minus 4 cannot equal 0, then we have the x cannot be equal to 4. And just give you a bit of a visual. Okay, so we had the centerpiece numbers with negative and positive 4. And with negative and positive 4 excluded. Because they have like holes on the sections where negative and positive 4 are located. And in terms of what is going to make up the domain, to be everything else that we have in x. Okay, and so we have with the continuous activity. So you have at the extreme ends, okay, we have left arrowhead, you have signaling the approach to negative infinity, right? Okay, you have the approach to positive infinity. Okay, and what I'm going to do here is that for the domain, and we have with the, just taking what we have with the left hand section. Okay, so we have again, infinities are balanced, so they will stay in parentheses. Now for this first first leg, so to speak. You have between negative infinity, approaching but not including -4. Okay, -4 is not included. And then we have this strip or line segment in the middle. So you have values of x, okay, such that -4 is less than x is less than 4. So you have this middle section. And again, so the parentheses indicate that negative and +4 are excluded. And then we have for the remainder, as we go past 4, so you have an interval notation. So this will represent the set of values x greater than 4. So we have for the domain of this ratio, this is the interval notation that will signal that we're going to have everything in the real number system with the exclusion of negative and +4. So you have those values less than -4, those values between but not including negative and +4, and those values that will be greater than 4. So that will be the interval notation for the domain of this expression. Now, looking at another case here where restrictions can come not only from fractions but also from radicals. And if we have, let's say, if we have f of x is equal to the square root of x minus 7. Again, we're not looking at complex numbers, just real numbers only. So, and the type of radical we have is an even root, and because of this, with the square root of x minus 7, x minus 7 cannot be negative. For an even root. It can be for an odd root, like cubic root, fifth root. So for the terminology we're going to have here, so x minus 7 cannot be negative for an even root. And in terms of the symbolic notation, okay, now x minus 7, it can be equal to 0 because you can have the square root of 0 in direct fashion, and it can be positive. So we have, in this particular case, for just the inequality notation, we have x minus 7 is greater than or equal to 0, and pinpointing what we will have for the domain for this function. Okay, so if I add 7 to both sides, we're going to have the x is greater than or equal to 7. And just looking at what we have visually. Okay, so we have the equal parts in the inequality telling us, okay, that 7 is included, and the rest of the values will be greater than. Okay, so you have, in this case, you have a ray that's going to go out to the right, and we have continuously running out in the direction of positive infinity. So we have for the interval notation, okay, so 7 is included, and so in the interval notation, okay, we'll have a bracket around the 7. And again, because infinities are boundless, we have going out to infinity, and again we have the parenthesis around the infinity. So this short notation, in comparison to what we just encountered, okay, that is going to be the entire interval solution for this particular radical function. And let's say that, sort of serving as a reminder, okay, if we have, let's say, that f of x is equal to the square root of 8 minus 2x. Can we have a square root? Okay, so you have 8 minus 2x cannot be negative. Okay, and because we have the square root given in direct fashion, now 8 minus 2x can be 0, and it can also be positive. So in this case, we have 8 minus 2x, and we can establish an inequality. Okay, so 8 minus 2x is greater than or equal to 0. So 8 minus 2x can be positive, or it can be equal to 0. And looking at solving what we have for x, that will keep this function defined in the real number system. Okay, and if we take 8 away from both sides, okay, so have negative 2x is greater than or equal to negative 8. Okay, and so we have another run-in. Okay, and this is with the inequalities. And if I'm looking at multiplying or dividing by a negative, okay, if you multiply or divide by a negative, the direction of the inequality is going to change. Okay, so we have transitioning from greater than or equal to less than or equal to. And here we're going to have negative 2x over negative 2 becomes x. And we have that x is less than or equal to 4. Okay, so just looking at it, say graphically, so you have the equal sign. So 4 is included. Everything else is going to be less than. Again, we have the lower limit, okay, in the direction of minus infinity. And so for what we'll have in this case, so going from negative infinity, and again, negative infinity is in the parenthesis, and we have approaching and including 4. And so 4 is going to be in the bracket. And now, separate case, but also a special case. And this is where a twofold situation can arise. And say we have f of x is equal to 3 over the square root of x minus 2. And what I mean by a twofold situation, okay, is that we have a 3 over the square root of x minus 2, okay, because we have a radical x minus 2 cannot be negative. But also because x minus 2 happens to also be in the denominator. X minus 2 cannot be 0 either. So it can't be negative, can't be 0, so x minus 2 must be positive. And just the inequality set up on these. Okay, so you have x minus 2. And if x minus 2 is positive, and I express as a comparison to 0 inequality, well, x minus 2 is going to be greater than 0. No equal sign this time around because, again, x minus 2 is in the denominator, and the denominator cannot be equal to 0. So for the defining inequality referencing the domain of this particular function, we have x minus 2 is greater than 0, and upon adding 2 to both sides, we're going to have the x is greater than 2. It just has a quick graphing sketch. So on 2, and so you have a hole at 2, since 2 is not included. And again, the activity we have exclusively going out to the right. Approaching infinity. So you have with the interval notation, okay, so we have going past 2, so you have 2 in parenthesis, and we have approaching infinity, and again, infinities stay in parentheses. So this will be your interval notation for the domain of this particular radical yet rational function. Okay, all right, and now looking at what we have in the case of functions, okay, and they're going to cross over to equations, and especially linear equations. And now for this next section, okay, so you have with linear equations and 2 variables. Okay. First of all, okay, in the development to linear equations and 2 variables, and there'll be various formats, and one foundation is going to come from if it is not provided. Okay, we have in the determination of the slope of a line, and for the slope of a line, say the slope m of a line that passes through or that runs through. So you had to pass through 2 points. And we'll just label as x01, y01 for the first order pair. Now for the second order pair, we have x02, y02. And we'll have that m is equal to, we have y02 minus y01. All over x02 minus x01. Okay, so you're looking at vertical change with respect to horizontal change. And have with the conditions that x02 minus x01 cannot be equal to 0, or in essence, that you cannot have the same x values in order for the slope to be defined. Okay. And I'll just mention, okay, if you have that if you have that x01 is equal to x02, then the difference that we have in the denominator setup your difference would be 0. And for what you would have in consequence is that the slope would be undefined. Because of the 0 denominator. And there is a kind of line that does have an undefined slope. Okay, it'd be just like only change in y, but no change in x. So your line will be running up and down. Since your x value is going to be the same, you can change your y value, so you have moving up, moving down, and so the line would be vertical. Okay, and just a case of what we have regarding slope. Okay, so again, slope m of a line passing through 2 points, x01, y01, and x2, y2. You're looking at the ratio of the change. Say we have, some books might have it as y01 minus y02 all over x01 minus x02, but you want to have the same sequence in accordance to the subscripted value. Okay, so in other words, you don't want to have crisscross like y2 minus y1 over x01 minus x02. Chances are you will end up with the additive inverse of what was intended. Okay, now for what we have, so you have as an example. Okay, so you have okay, so you have determining the slope of a line that's going to go through and we'll say we have with our order pairs, so say we have -1, -4, and 3, 6. Okay, and you can determine what we have here with the slope formula. Okay, so you have -1, -4, and we have 3, 6. And again, just being careful with the labeling. Okay, so we have m is equal to y02 minus y01 all over x02 minus x01. Okay, so again, each ordered pair will be of the form xy. So say that since -1, -4 we had given first, we have x01, y01, 3, 6 given subsequently. So you have x02, y02. And if I were to substitute accordingly, okay, so your y02 minus y01, we have y02 is at 6. We have minus y01. Now your y01 is at -4. So you have a subtraction of a negative. Now for x2 minus x1, so your second x we have at 3, minus the first x value, which we have at -1. So you have another subtraction of a negative. So you have 6 plus 4 all over 3 plus 1. So you have 10 over 4, and 10 over 4 is reducible to 5 halves. Okay. So that is going to be the slope. And just for the pattern, say if you were to read in order from left to right, you would have a bit of a cycle of like going up 5 and out to the right 2 units. And just giving a little bit of a visual. Okay, so we have with our points, okay, so you have like -1, you got -4, so just have labeling a point. Okay, so you have -1, -4, and the other one we have at 3, 6. Okay, and if I put a straight line through this, yeah, we do it like this. Okay, so you notice you have -1, -4, and 3, 6. And in terms of the slope, okay, so if I have a cycle going up 5 units and out to the right 3 units, okay, what's going to happen here? So you have like going up 5 units. And then I have going up, let's see, I'm going to line this up. My bad. Trying to draw this in proportion. Not having much success, but we'll make amends. Okay, so if I go up 5 units, I would go through -1 here. So you have going up 5 units. Then you have going out to the right 3 units. And staying on this line. So I have like an intermediate point at 1, 1. And if I were to go up, let's say another 5 units. And we have in this particular case, right, so I have going from -1, -4 to 3, 6. Okay, so up 5, right 2, and then just repeating the cycle, up 5, and have going to the right 2 units, so I have like 3, 6, and if I followed the same cycle going up 5 units into the right 2 units, I would end up at, in this case, this would be like 5, 11. Okay, and so this is just a visual illustration of the slope and how we progress from one point to the next. And sometimes you might have a little bit of a stretch. We're just in the gradual process, kind of doing a granular breakdown. Okay, like in this case, you have like in the big picture, I went up 10 to the right 4, but up 5 right 2, up 5 right 2. Okay, just again, just a more incremental pathway, but still getting to the final destination. And it will be from the slope, okay, that we will have the foundations to various types of equations. We have like the point slope form of a linear equation, as well as the slope intercept, and we'll be looking ahead to those items. Again, just some reminders. Okay, now again, test number 1 is due tonight, and some of you might have already completed, and again, I'm going to look over each of the exams and just apply partial credit maybe in venues where the software did not, and I'll look at those items more closely than I have the regular Alex homework. And just some items here. Let's see, just adjusting for section 1-3. Okay, I have this available, and I adjust the due date to Saturday, February the 13th at 11:59 p.m. That again is on Saturday. And section 1.5. Okay, that is due next week, Monday, February the 15th at 11:59 p.m. And I do have video simulations for those sections available in the weekly notes tab, and items to go ahead and be looking into. And we have regarding the functions and functional values, as well as the domain. Okay, be looking into numbers 44, 47, 56, 100 parts A through C, as well as 104C from page 147. And from page 162, you can go ahead and be looking into numbers 27, 30, 39, 42, 52, 62, and also number 8. And if there are any questions, I will stick around for the next few moments. Otherwise, we'll pick up next time on Wednesday. Have a great day. You too. Thank you.